Right. Good morning, ladies and gentlemen. It's my great pleasure to be able to introduce you to this morning's speaker in the Game On Spring Data Science Festival. This has been running 10 years, I'm reliably informed, more than that in a number of sessions. The quality's been great over the years, and it's lovely to see so many people coming back again each time. For those of you who didn't make it to the earlier session this morning, can I just remind you, pop your phones on silent. If the fire alarm goes off, it's not a drill, so please follow the fire exit signs, either the way you came in or to the right of the room as you go out. All of the talks, or practically all the talks, are going to be recorded. They'll be available on the DSF website and on the YouTube channel if you miss anything or you just want to review. This is a community effort. It's put together by the speakers, all of the volunteers, and all of the companies that support us. In particular, we're really grateful to the support from our sponsors, which is Data Idols, who are the main organizer of the event, Key, Statsig, dunnhumby, Zerv, Streambased, Ovo, Checkout.com, National Grid, and Man Group, Founders 500, and of course CodeNode, who provide the venue and do such a great job with the AV for the event. I will remind you that in the back of your booklet, there's a little voucher for free popcorn at the stand downstairs, and that we've got upcoming sessions coming in September for a new Careers Day and November for Winterfest. And finally, there's a DSF competition up on all the signs outside where you get the chance to win a free iPad just for tagging us on LinkedIn. So, it's my great pleasure to move on to our first speaker in this room. Jerry Mundondo at StatSports is going to be talking about mastering synthetic data generation in sports analytics. Jerry is a data scientist who began in marketing data science and has since specialized in sports analytics. He combines traditional data science approaches with large language model approaches to address real-world challenges in analytics. He's focused on limited data scenarios, and is going to be talking about using synthetic data generation together with advanced analytics in the sports domain. So over to Jerry.
Morning, everybody. Thank you for joining me for this talk, and thanks to DSF for putting on another amazing event. I know it's just started, but no doubt it will be great. Just some context around myself. My name is Jerry Mundondo, data scientist at StatSports. And I have an undergrad in sports science from Swansea Uni and a master's in data science from the University of Liverpool. So that's how I got into the sports data science space. And like Charlie said, I have experience before getting into sports data in a more marketing sort of space. So what are we going to cover today? Three main things. Some very basic sports science principles. The problem that we've all dealt with as data professionals, which is a lack of data. And finally, how making counterfeits of the Mona Lisa can reduce injuries in baseball players. So context around where I work and what we do so that this presentation actually makes sense. So you may have seen athletes wearing these black vests when they're training, sometimes in matches. At the back of those black vests is a tiny GPS unit, and that's what we provide. And it allows us to collect data, 200 metrics at 100 hertz, so quite large quantities of data. So by the end of training, we have a lot to go through. So examples of the metrics that we collect are accelerations, decelerations, distance covered, and a lot more. But the key question is, why do those metrics matter? And it really just does come down to this, load monitoring, which is just tracking how much strain is being put on the body. Because just like how if you overwork your car, it will break down, the same thing happens with the human body, where if you overwork a person, they also break down in the form of an injury. Okay, but why do we care about load monitoring? Let's go a little bit more in depth. This is the golden triangle of why we care. Availability, which is the injury element that we just touched on, performance, and lastly, cost. So let's start with the availability aspect. And there's three main things. Firstly, by tracking those metrics, we can keep an objective measure of how much strain the athlete is being put under and ensure that the athlete is never overworked, never gets injured as a result, or reduce the odds of injury, rather. Maybe even more importantly is return to play. once an athlete is injured, let's say they have a hamstring injury, the last thing you want is for them to return to their first training session and try to run at 100%, because that would lead to re-injury. But the issue is, research has shown that athletes are so tied up in their identity as an athlete that if you leave it up to them, they would rather try to train whilst they're injured or even go to matches whilst they're injured rather than go to the physio room. So by tracking those metrics, we keep an objective measure of whether they are ready to return to full play. And then the last element on this injury management perspective is long-term health. Again, research in America has shown that athletes who get injured during their career are more likely to need surgery once they retire. And if they get a surgery after they retire, they actually have a lower quality of life than the average American. So it's not great. And moving on to performance. Tracking those metrics helps us with a sports science principle called training periodization. Essentially, it's impossible for an athlete's body to be at 100%, 24/7, all year round throughout their career. So by tracking those metrics, we're able to periodize so that they can peak when it's most important. So for an Olympic athlete, for example, they will peak every 4 years at the Olympics. Contrast that with the tennis player who needs to peak 4 times a year, which is the 4 Grand Slams that are in tennis. And also general performance monitoring is important. Again, tracking the metrics helps see, for example, if a strength and conditioning coach is trying to improve a specific element of the athlete, like the number of sprints they make in a match. Without an objective measure of that, you'd just be relying on the eye test, but tracking those metrics helps us to ensure that it's objective. And the last bit of that triangle we're talking about is performance and financial. As you can see on this nice big table that I'm sure you can read from the back, this is the important part. This table shows the payouts from the Premier League to Premier League clubs at the end of the 2023-24 season. So essentially, the higher up you finish, the more money you get. And the difference between finishing 12th and 13th, for example, can be close to £2 million. So if you ensure that your players are never injured by tracking their metrics, you're more likely to have your best players available and likely to finish higher up the table, better payout. Trust me, this is all going to circle back around to data science. We're going to get there. The business perspective, the last element is this. We know at the very highest level, players can be on quite big wages. If the player gets injured, let's say, for 8 weeks, guess what you still have to do for 8 weeks? You still have to pay them, right? So you're paying a lot of money for somebody who's not even available to contribute. Okay, last thing on this sports science-y element is we have 2 load profiles in general. So we have what we call open sports. These are things like football, basketball, rugby, or invasion games. So with these, the referee blows the whistle, then everybody can move where they want, and it's fairly random. These sports are quite mature in terms of tracking the metrics. So things like distance covered, sprints, jumps, we have validated ways of doing all of this, so that's fine. But our example for today is the realm of baseball, which is what we call a discrete sport, where nothing is happening until a specific event occurs, and that event is throwing a pitch. Once the pitch is thrown, the batter swings, fielders do their thing. So that's why it's called discrete. But here's the thing. There is some running in baseball, but it's not the main load. It's not like our open sports, where that's the main load. Instead, we have 3 types of load that we're focusing on. Pitches, swinging, and throwing. Our main focus today is pitching. So the most common injury in baseball is called a Tommy John injury, or the more scientific name is a UCL, ulnar collateral ligament. Basically, it attaches the forearm to the upper arm, and it's quite common because of this. Pitchers, when they throw, apply a lot of strain on that ligament. That's just one throw. In a single match, they can throw up to 100 times or just over 100 times. And that's just in matches. In training, leading up to the match, probably a lot more than 100. So you can see why that could be a potential issue. So imagine you've just signed a pitcher on a huge contract and they get a Tommy John injury 6 months in. It wouldn't be ideal, right? And that injury is so commonplace, there's been a lot of research done into the impacts of it. And in this paper in particular, they looked at pitchers before they got injured, and then 1, 2, and 3 years after their injury to see what the differences would be. And it was stark. So you can see 3 years after getting surgery for this injury, their pitch count had decreased by 45%. So before, if their body could handle 100 pitches in a match, that was now down to 55. Not only was it down to 55, those pitches were slower, and they had less variety in the types of balls they were able to pitch. And just to really drive this home, only 1.6% of the pitchers returned to play within a year. After 3 years, 82% returned. Sounds good, right? But less than 30% of those were anywhere near their pre-performance level. And looking at all the metrics, the researchers concluded that 3 years after a Tommy John injury, pitchers only contribute 50% of the value they did before injuries. So, finally, to the data science-y bit. The task I was assigned with was developing an automated algorithm to detect the number of pitches in a session. Because if we have that algorithm that can do that, we're then able to monitor the load in these pitches and reduce the odds of those devastating injuries that we've just touched on by looking at things like number of pitches, pitch intensity, rotational load, and so much more. So what was the issue? We've all been here as data professionals. A lack of data, it's not a new thing. So I was in the dreaded triangle. Needed to build an algorithm to prevent injuries. An algorithm needs data, and how could I get more pitching data? Asking pitchers to go through more pitches, which is just increasing their odds of injury. So it didn't really make sense to increase their load to hopefully one day reduce their odds of injury. So what is a way to solve this? Synthetic data, which is essentially artificially generated data that is designed to mimic real-world data as closely as possible. So how could I go about doing this? Well, are you a data scientist if you don't try use Gen AI for everything? Like I said before, I was in the sports realm, I worked in marketing, and we had to do a lot of text-based work, like building sentiment analysis model. So in those cases, it was actually highly effective, because let's say I needed more text with negative sentiment to build a model around that. I could just feed it into a model. There we go. No problem, right? I had a feeling this wouldn't work on time series GPS data with a lot of metrics. And I was right, because the values that it generated were highly ineffective because it didn't respect the realms of physical possibility. So if pitchers were throwing at the levels that Gen AI suggested, they would have a lot worse than a Tommy John injury. It also didn't respect the movement and the sequence, the X, Y, and Z movement of the GPS occur in usual pitches. So I had to look for a different approach. Variational autoencoders, or VAEs, showed a lot of promise for my use case, but I did have a few issues. It was good because it was fairly light and easy to train. However, it also at times did not respect the realms of physical possibility, and it lost a bit of the granularity in the pitch data. But the biggest issue that I had was, after a while, all the synthetic data that it began to generate began to converge towards the average. I should say this was a vanilla VAE, so if I had done a little bit more fine-tuning, I think I could have had some more luck, but this just was not the route that I wanted to pursue. So I had to take a step back and think about what we're trying to achieve. We want synthetic data, which is the same as fake data, which you could say is kind of like counterfeit data. And who in the world is the best at generating counterfeit things? Well, for that, we have to visit the world of organized crime. And more specifically, people who make fake art, or art forgers is apparently the official term. Their whole shtick is becoming as good at generating this synthetic art as possible. So why are we talking about art forgers? Well, Data science gets a lot of inspiration for its algorithms from the real world. And it turns out there is an algorithm that uses this art forger dynamic. And that's what we're going to be focusing on. So how does this algorithm work? Okay, suppose we have a two-person team. Their entire goal in life is to generate fake art and make millions before eventually getting arrested. But that is their goal. But here's a key thing. Their minds have been completely wiped. They don't know what art looks like. They just know my goal is to be able to generate synthetic art. So our two-person team decide to split up their responsibilities. One says, okay, I am the artist or the generator. My entire goal in life is to get really good at painting counterfeits. The other guy says, okay, I'm the judge or the discriminator. My goal in life is to become as good at detecting counterfeits as possible. Because here's the logic. If the judge is world-class at being able to detect counterfeits, if our artist is then able to consistently fool our judge, that means our artist is pretty good at generating synthetic art and can hypothetically then generate near infinite amounts of synthetic art or synthetic data. So to make this example more clear, suppose their task was to generate a counterfeit of the Mona Lisa. Remember that our two-person team, they've had their brains wiped. So our judge doesn't know what the Mona Lisa looks like. So initially, the judge receives very basic training, where they're shown the Mona Lisa and a literal bunch of scribbles and taught to differentiate between those two. You don't really have to be great to differentiate between those, do you? But that's the very basic training they initially get. Now remember, our artist does not know what the Mona Lisa looks like, because they've had their brains wiped. But our artist tries, comes up with a bunch of scribbles, goes to our judge and says, is this the Mona Lisa? Our judge, even with their very basic training, is 99% sure this is fake. So this then triggers a feedback cycle where the artist then has to go and improve their art, which is the algorithm updating their weights so they can get closer to the real thing. Our artist iterates, comes back with this. Still not great, better than scribbles, right? Our judge is still pretty sure it's fake. Remember, our judge isn't great, so only 95% sure, dropped by a couple percent points. I don't know, maybe the head of the flower looks a bit like a head. Maybe the stem's like a neck there, so that could have made it less sure, but the judge is still pretty sure. Again, signals to the artist to improve. Artist iterates, comes back with this, added some color. I mean, the Mona Lisa has color, so judge is less sure, but still pretty sure, 90%. The feedback cycle is triggered again. But then maybe the artist comes back with something like this. It's sort of humanoid. And remember that our judge was only given very basic training. So because it's kind of human, our judge gets confused and says, okay, I'm only 49% sure that this is fake. So this is now a signal to the judge now to go and improve their ability to detect between real art, the Mona Lisa, or now it's not just scribbles, but it's a vaguely humanoid stick figure. So I have a few more of these examples, so I'm going to try and make it a little bit more interactive. I'll be asking you guys who needs to go and improve, okay? So our artist has this, our judge has been trained better, now our judge is 99% sure it's fake. Who has to go and improve and update their weights? The artist. Artist does the same, comes back with this, getting a little bit closer. So because our judge was now trained between the Mona Lisa and the stick figure, this might throw the judge off a bit. Only 30% sure that it's fake. Who has to go and improve? The judge. Our judge is now better, can tell this is fake. Who has to go and improve? Artist. So the artist iterates again, and you can see slowly through this consistent feedback cycle, our artist is getting a lot better. So this sketch is now somewhat close. I can see the whispers of the Mona Lisa in there. So the judge is unsure. 49%. Who has to go and improve? The judge. Artist comes back with this, edging a little bit closer to it. Judge is still 85% sure, so still pretty sure that it's fake. Who has to go and improve? The artist. Something better. Again, judge is still pretty sure it's fake because their last training has been helping them differentiate between the Mona Lisa and now a pretty good sketch. So now the artist has to go and improve because the judge, still not great, but is able to detect it's a fake. So they have to go and improve. And you can see how this iteration is slowly pushing the artist closer and closer to the real thing. So of course, this is going to be able to fool the judge. So who would then have to go and improve? The judge. The judge is a little bit better now, says it's fake, 99% sure, so of course this is the signal for the artist to go and improve and update their weights. Same thing happens here, artist has to go improve, iterate, because the judge is still pretty sure it's fake. So this iterative feedback cycle continues and continues until eventually the artist will come back with this, a near replica of the Mona Lisa. And the judge can no longer differentiate between the synthetic art and the real art. So the logic now is hypothetically, the artist or the generator could then pump out a bunch of synthetic art that is indistinguishable from the real thing. So back to sports data. Why are we talking about this? The algorithm we've just discussed is called the generative adversarial network. And it's usually used in generating synthetic image data, but it has many other use cases. There's specific GANs for text data, for video data, time data, but the one that I used is called a CT GAN, conditional tabular data, because that GPS data of the pitches was tabular, so that's the one that I opted to go with. So hopefully that little illustration of how the GAN works was clear. However, we are data professionals, so we need the actual architecture. So this is what it looks like. We have our discriminator there, our generator there, and this is the first phase iteration where we get the real images and literal random scribbles to start off with. That's fed into the discriminator, and based on the decision probability, it will affect how much each one needs to improve, because on each iteration, both the generator and the discriminator update their weights, but it's just whoever was wrong updates their weights more. So that is actually the algorithm that I used to generate synthetic pitches, so that I no longer had to go ask pitchers to go through 100,000 times just so I have data for my algorithm. So was this synthetic data any good? Well, just a quick visual way of demonstrating this. Well, this is a KDE. So what we have here is, in orange, is the synthetic data, blue is the real data. So for example, here for peak speed, you can see in the real data, just over 70% of the time, the peak speed was around 3, whereas for synthetic data, it's around 50-ish% of the time. So you can see it's not an exact replica because that would be overfitting. It might just be copy-pasting the existing pitches. But I'm sure you can see just visually, it's a pretty good estimate of the general patterns of what the pitch GPS data would look like. Of course, in reality, you'd want more statistical measures of checking if the synthetic data is good, but this is just a way of visually representing it. And on that in that same vein, the synthetic data generator generated both pitches and non-pitch data, because in a training session, the pitcher would, yes, pitch at times, but then in between they'll be walking around. They might even do a bit of batting practice, so we need to be able to tell between those. So there's pitch and non-pitch data. So using the limited real data, I built a model to detect pitch events. And then the synthetic data generator generated both pitch event and non-pitch event. So the logic is the model built on the real data should perform pretty well on the synthetic data if it is a good representation of the real data. And you can see by the numbers down in the table there that it was a pretty it was pretty accurate. And just the last thing that I was concerned with was physical realism, because we don't want a repeat of people's arms falling off. What this is for every variable, let's say the X movement of the GPS during a pitch, suppose the minimum was always between 2 and 8 for the real data. The last thing you'd want is for within the synthetic data, for it to be a lot less than 2 quite often, or a lot more than 8 quite often, because that would be a signal that it's not respecting what the real data looks like. So you can see on this graph for all these metrics that almost never happened. It only happened for these 2 metrics, and even then it was less than 2% of the time. So essentially the synthetic data generator did quite a decent job. So some key takeaways. It's important to always combine data science methodologies with your domain knowledge. So in my case, it was making sure that the physical realism is respected when generating synthetic data. In your use case, it might be slightly different. You should consistently augment your synthetic data with real data whenever possible. So don't just build your synthetic data generator once and then use it forever. Instead, now I would continue collecting the pitch data, but rather than asking a pitcher to throw 100,000 times in a single session, it would be the 100 they would have thrown anyway. So slowly, more and more real data gets added, which means the synthetic data generator gets better, as well as the model itself. And always try and validate different models for your use case. Don't always just go with the first one that you try. Any questions?
Thanks, Jerry. That was a really good talk. I think we had a question down here.
First of all, really, really interesting presentation, and it's quite refreshing to see it being used in a less traditional domain. The question really is around the confusion matrix thing that you had, as well as some F1 scores.
Yeah.
Could you just very briefly just kind of clarify what you're doing here? So are you comparing? Typically this would be used for classification.
Yeah.
Yeah. So is that what you're doing here?
Yes. So I trained a model on the limited real data, and then the synthetic data generator generates both pitch and non-pitch events, and a label for each one of those, of whether it's pitch or non-pitch. So then run the real model on that synthetic data to see if the real model performs well on the synthetic data, and if the synthetic data is self-labeling its data accurately.
Cool, thank you. Sorry, I got one more question. Other question is, typically what you're doing here is obviously you're trying to using the generative model to sort of somehow generate the distribution of what kind of reflects reality.
Yes.
And typically you could use KL divergence as a way of comparing what could have been the actual distribution in the real world compared to what's the synthetic kind of version. Can that also be used as a way to measure how close the synthetic data was to the actual attribute that you're trying to synthesize in the first place?
That's interesting, because I hadn't used that, so I can't speak to that too well, but I might actually run that as well after this, so that's actually a great idea you've given me.
Really good work anyway, by the way. Thank you very much.
Thank you.
Thanks, Jerry. Amazing storytelling. I love the example. I'm not from this domain, so just trying to understand. The model you've built, it's trying to predict in the GPS data, it's trying to predict the pitch and non-pitch events.
Yes.
But then what is the next step? How do you actually help athletes to avoid injuries?
Oh, perfect.
And how do you kind of try to predict the injury event? And what's the next step, basically?
So the next step would then be developing different measures such as rotational intensity, pitch intensity, and other sort of metrics that are able to see how hard the athlete is working. And then based on that, because you're able to automatically detect it, the coaches on the side will be able to keep a track of when a pitcher is nearing their red zone and likely to get injured, and pull them out of training or reduce the number of pitches that they were scheduled to do.
Sorry, just Maybe a follow-up. And
Yes.
when they are nearing the red zone, how would you know that? Do you also use synthetic data to generate would-be injuries to kind of see where the red zone begins?
So that would be more of a research element of, because we have relationships with different sporting organizations, it would be more of a research of slowly seeing where that red zone is, identifying it, and the factors that contribute to it, because I'm sure it will vary by athlete. So once the sports science team would then essentially establish where the red zone is and how that comes about.
Thank you very much.
Sure.
Thank you very much. Just to clarify, what is the 0-1 factor accuracy of
0-1. To clarify, what does...
in the table?
Yes.
0 and 1 to 30.
Okay, so the 1 is a pitch, 0 is a non-pitch event. Sorry, just I need to repeat the question so everyone hears. He was asking, what does the 0-1 mean here?
Yeah, does it correspond to the matrix above, or is it different models?
So they do correspond. So here, a 1 means that it was a pitch. This is a true label. So in actuality, it was a pitch. And here is where the predicted label, the model also predicted that it's a pitch. So here it got it correct here. These two diagonals, it got it wrong.
Okay,
Yeah.
thanks. Just to follow up on
Yes.
that, did you do any testing to see what the performance of your model was built on just the synthetic data, just the actual data manipulations?
Sorry, could you...
Sorry, I was just curious, did you build different models using just the synthetic, just the actual data, just like variations? Like, was there a difference in?
Yes, so I did build one using just the real data. Sorry, let me repeat. He's asking if I built a model on just the synthetic data and just the real data and the variation between those. I did build a model on just the real data. It performed well when only detecting pitch events versus non-pitch in terms of walking and what have you. However, when it was pitch versus, let's say, swinging, it was less accurate because those are both high-intensity activities. I did not build one on just synthetic data, though. But then detecting between pitches and just non-pitches is fairly straightforward if it's like somebody walking or somebody pitching. Where we need more data to differentiate is when it's pitching versus swinging. So that's why we would need the synthetic data to make sure we have high amounts of both variables.
Yeah. So firstly, again, good presentation so far. So my question is, when do we know when to use synthetic data and actual real data? So is there like, if we have actual data, do we use synthetic data as well? Or is we only use the synthetic data when we don't have data?
So it varies case by case, but in my opinion, if you have enough real data is better than synthetic data, always, pretty much. So if you have enough real data, always go with the real data, for the most part. And then when you need to augment that real data, when your model's not performing well enough, you just don't have enough data points, that's when it's a good idea to introduce some synthetic data.
That makes sense. Yeah. Thank you.
So you mentioned that you detect, like you can predict injuries, like a pitch that induces the injury is kind of a one-off event. So you might not have a lot of data for when the pitch, like when a pitch that is thrown can produce an injury. So how do you define a range that, okay, when the data is between this range, like you mentioned the red zone.
Yeah.
So how do you define that with the injury data being very sparse and very like one-off event that could cause an injury?
Great question. So I think that, like I was saying before, that would be more of a research project for the sports science team to try and define when an athlete begins to be at risk of that injury. It's yet undefined because, like I was saying, in these discrete sports, it's less mature in terms of monitoring the load in that aspect. So it would be more on the sports science team to sort of research that. And I think whilst for something like a pitch, it is a one-off event that leads to an injury, I believe the build-up of having that event happen over and over is what leads to the injury rather than they threw it really hard or really specifically on one occasion. Because that's what, with soft tissue injuries, it's usually a buildup of load over time rather than an impact injury like a bad tackle that breaks your leg. That's usually like a one-off, couldn't have seen it coming sort of injury.
Thanks for the talk. Really good, really interesting topic. And I was just thinking about what you spoke earlier about, obviously, this example is in a discrete setting, but in terms of other sports are more open. Take football, for example. Mm-hmm. Would you take the same approach of finding, because in this case you've done pitches and non-pitches.
Yeah.
In football, obviously, load can, I guess, be defined, could be multiple things, running with the ball, kicking a ball. Would you break it down to multi-classification in that case, or would you still try and zone into one area?
I think the thing with football and rugby, the open sports, they are quite mature, so the algorithms of how to detect it, they already exist pretty much. But with those, for the most part, we are looking at running events. So it's like jogging, sprints, decelerations. So it's all one motion, and then it's different thresholds of when a jog becomes a sprint, how quickly the velocity has to change for it to be a deceleration, rather than classifying separate discrete events.
Like high intensity?
Yes.
Okay.
Yes.
Thank you.
No worries.
Hi there, thanks. Yeah, excellent talk.
Thank you.
I had a very quick question. What's an invasion sport? And then
Yes.
the follow-up is all this data being collected by a single kind of sensor located in the back?
What was the first question?
What's an invasion sport?
Oh, invasion sport. So that would be, I won't scroll all the way back, football, rugby, any sport where you're trying to score in another opponent's goal or area, it's called an invasion sport because you're like invading their territory. That's how you score a point. It's just the umbrella term for all those sorts of sports. And what was the second question?
So all this data is being captured by a GPS and inertial
Yes.
sensor on the back?
Yes.
There's no kind of wrist-mounted sensors or anything like that?
No, not at present. At the moment, it's just on the back.
Does it vary between kind of people of different sizes? It's elasticated. It's moving around a lot, etc.
So it's supposed to be quite a tight fit. So the vest itself comes in different sizes, but within each size it will be quite a tight fit. So it should stay pretty stationary against the vertebrae.
Okay, got one last question.
First of all, thanks for the talk. It was really interesting. Just on this slide in particular, so you showed the GAN architecture, and obviously you're basically pitting the two models against each other to say which one needs to improve.
Yes.
For that aspect, does that require like human intervention to say, right, you assess the two models and see which one needs to improve, or is that sort of done as part of the architecture itself?
So it doesn't require any human intervention. Just once you start, it sort of gets in a self-feedback loop. So you just start it and run it.
Does it sort of have like the inputs known that it's a fake image or not, and then from there decide which one needs to improve, or is it?
Yes, so it knows the real images, and then from the generator. Wait, could you?
As in, so if we like maybe go back to the baseball example, so you're giving it some real data and you're giving it some random generated data.
Yes.
And it's sort of assessing between, it's being given both of those and then saying
yes,
which one needs to improve or the other.
Yes, so its goal that it's technically trying to see if the fake data is a sample from the real data set, because maybe one thing I didn't capture too well is that it wouldn't be trying to generate one image. There would be a bunch of real images, and it's trying to see is the fake data likely to come from the original data set of these thousands of real images.
Great, thanks.
Okay, it's time for coffee. Let's thank Jerry again.
Thank you.